The release of two new images of the interstellar object known as 3I/Atlas on November 5, 2025, adds an intriguing new layer to an already puzzling astronomical case. These images reveal a compact source of light that lacks a clearly defined cometary tail, a feature that would normally be expected if the object were behaving like a typical comet after a close passage to the Sun. What makes this observation particularly striking is that the morphology of the coma appears not to differ significantly from its appearance several months earlier, when the object was imaged by the Hubble Space Telescope on July 21, 2025. This apparent morphological stability raises serious questions about the physical processes governing mass loss and outgassing in this interstellar visitor, and challenges some of the assumptions astronomers commonly make when interpreting cometary activity. From a theoretical standpoint, momentum conservation provides a powerful framework for understanding how mass loss should manifest observationally. When a comet approaches the Sun, solar heating causes volatile materials to sublimate, ejecting gas and entrained dust into space. This process not only creates a visible coma, but also produces non-gravitational forces that can measurably alter the object's trajectory. By analyzing these deviations, one can estimate the amount of mass that must have been lost during perihelion passage. In the case of 3I/Atlas, such an analysis suggests that more than 13% of the object's total mass was shed as it passed closest to the Sun. For a typical comet, this level of mass loss would be dramatic, producing a dense, extended coma and a prominent tail shaped by solar radiation pressure and the solar wind, unmistakably pointing away from the Sun. Yet, the November 5 images show no such tail. Instead, the object appears relatively compact, with a subdued coma and no obvious asymmetry or extension in the antisolar direction. This discrepancy between theoretical expectation and observational reality lies at the heart of the mystery. If the inferred mass loss is indeed correct, then the absence of a visible tail demands an explanation that goes beyond standard cometary behavior. One possibility is that the material being lost is not dust-rich in the way solar system comets typically are. Dust particles are highly effective at scattering sunlight, which is why cometary tails are often so visually striking. If instead, the mass loss from 3I/Atlas consists primarily of gas with very little dust, the resulting coma might remain relatively faint and compact, even if the total mass loss is substantial. Another possibility involves the size distribution of the ejected particles. If most of the solid material is released in the form of relatively large grains or chunks, solar radiation pressure would have a much weaker effect on them. Larger particles would tend to stay closer to the nucleus, producing a more symmetric and less extended coma, rather than a long, sweeping tail. This scenario could reconcile a high mass loss fraction with the observed lack of a pronounced tail, but it would imply that 3I/Atlas has a very unusual internal structure or composition compared to typical solar system comets. The comparison with Comet Lemon is particularly illuminating in this context. Observed by one of the same telescopes only 2 days earlier, Comet Lemon displays exactly the features astronomers expect: a bright coma and a clearly defined tail pointing away from the Sun. This contrast is important because it rules out instrumental or observational biases as the primary cause of the missing tail in 3I/Atlas. The same observing setup that readily captured Lemon's tail failed to reveal anything similar for the interstellar object, strongly suggesting that the difference is intrinsic to the objects themselves rather than an artifact of the observations. The interstellar origin of 3I/Atlas may be the key factor here. Objects formed around other stars are likely to have experienced very different thermal, chemical, and dynamical histories than comets formed in our own solar system. They may contain volatile species that sublimate at different temperatures, or they may have undergone processing by cosmic rays and interstellar radiation fields for millions or even billions of years before entering the solar system. Such long exposure could alter the structure of the surface layers, potentially creating an insulating crust that suppresses dust release even when deeper volatiles are sublimating vigorously. In this case, significant mass loss could occur beneath the surface without producing the kind of dusty outflow that leads to a visible tail. Another intriguing idea is that the mass loss might be highly anisotropic, occurring preferentially in directions that do not produce a prominent tail from our vantage point. If jets of gas are oriented in such a way that their combined effect largely cancels out in the plane of the sky, the object could lose substantial mass while still appearing relatively compact. This would require a rather specific geometry, but it cannot be ruled out without detailed modeling of the object's rotation state and outgassing patterns. The broader implications of this puzzle extend beyond the specifics of 3I/Atlas. Interstellar objects provide a rare and invaluable opportunity to study material formed in other planetary systems directly. Each such object challenges astronomers to reconsider which aspects of cometary behavior are truly universal and which are artifacts of our solar system's particular history. The apparent mismatch between the inferred mass loss and the observed morphology of 3I/Atlas suggests that our existing models, largely calibrated on solar system comets, may not be fully adequate when applied to interstellar visitors. This realization underscores the importance of maintaining a flexible, hypothesis-driven approach when interpreting new data, rather than forcing observations to fit preconceived expectations. Equally important is the human dimension of this scientific process. The careful, transparent reasoning involved in analyzing objects like 3I/Atlas, and the willingness to openly discuss uncertainties and alternative interpretations, plays a crucial role in making astrophysics accessible to a wider audience. When complex ideas such as momentum conservation, radiation pressure, and non-gravitational forces are presented clearly and thoughtfully, they invite curiosity rather than intimidation. This has a powerful ripple effect, inspiring people who might otherwise feel disconnected from science to engage with it more deeply. The example of an 18-year-old student finding motivation and direction through exposure to such work is a testament to this broader impact. Astronomy and astrophysics have a unique capacity to spark wonder, precisely because they deal with questions that transcend everyday experience. The origins of planetary systems, the nature of matter beyond our solar neighborhood, and the physical laws that govern the universe at every scale. When these topics are communicated with clarity and intellectual honesty, they can help young people see science not as an abstract or inaccessible pursuit, but as a dynamic, evolving field driven by curiosity and critical thinking. In this sense, the mystery of 3I/Atlas is not a problem to be solved as quickly as possible, but an opportunity to think more deeply about how we interpret the universe. The absence of a visible tail, despite strong evidence for substantial mass loss, invites astronomers to refine their models and consider new physical mechanisms. At the same time, it invites the public to witness science in action, a process of questioning, testing, and revising ideas in light of new evidence. This openness, combined with rigorous analysis, is what makes astrophysics both intellectually robust and profoundly inspiring. Ultimately, whether 3I/Atlas turns out to be a gas-dominated object, a dust-poor relic of another planetary system, or something even more exotic, its true value may lie in the questions it raises rather than the answers it provides. By challenging established expectations and encouraging fresh thinking, it advances not only our scientific understanding, but also our collective appreciation of how much there is still to learn. For those just beginning to consider a future in science, such as a young student standing at the threshold of her academic journey, this realization can be transformative, offering both a sense of humility before the vastness of the cosmos and an invitation to take part in the ongoing effort to understand it.